Okay, welcome back. So let's start the next lecture. So in the last lecture, we were talking about halos. In particular, we calculated what is known as the mass function. So that is the number of halos per unit co-moving volume per unit mass range. So one part is this, where you now know in your universe how many halos will form at a given redshift and what will be their mass distribution also. But the next thing which we would be interested in is to study their clustering properties. So in other words, if I calculate the 2-point correlation function of these halos, what would I get? Now, naively, one thing is clear that high density regions will probably form more halos than low density regions. But then, if I calculate the 2-point correlation function, then will we find that that correlation function just exactly traces the underlying matter correlation function, which we know for what will that be? I mean, we know the form of the power spectrum. From that, we can calculate the 2-point correlation function. The question is, will the correlation function for halos be identical? Will it just fall on top of that, or what? Will it have any mass dependence? So these are the questions one is trying to understand. And this will become very important in what we discuss later. I mean, of course, in the first lecture, if you remember my slides, I showed you that different galaxies shows different kinds of correlation. So clearly, there is something interesting happening here. So till now, what we have been calculating, I called it DNDM. I'm just introducing another notation here. I'm calling this NM bar at Z. So n subscript m is nothing but DNDM. And I have put a bar because this is like average over the whole universe. Okay, we gave you one number per redshift for a given mass beam. What we are interested in is to calculate, if possible, this quantity. And through that, calculate the contrast in halos, which can be a function of x, m, and z. That is this quantity nm xz by nm bar xz. Sorry, there is no x here, z minus 1. And now if I just calculate the 2-point correlation function of this quantity, that will tell me how the halos are clustered. In particular, I can even do the clustering as a function of mass. Now, how to do this? So the idea here will be, let's see how it should look like. So imagine you have your universe, which could be a simulation box, it could be a real universe. And then what you do is you divide it into some grids. Uniform grid is something good to work with. And now you go and calculate, like you are doing in your tutorial, calculate the density in each of these grids through some way of smoothing the particle positions. You calculate the density. Once you calculate the density, you can calculate delta m. So for each point, you will have a delta m. And what you can do is you have delta m as like a function of uniform grid. You can Fourier transform and calculate the power spectrum, or you can try to calculate the 2-point correlation from here. So whatever you want to do, you can do from this. Now what we are interested now is I go to each grid and see how many halos are there. Maybe this one has many halos, this one does not, this one has 2, maybe this one has 1, again this one has many halos, and so on. So I want to see that what happens as a function of position. That is basically this quantity. Number of halos as a function of x. Now one assumption we will make here is that we will assume that these cells are quite large. They are large so that the density contrasts in these cells are small, and they are very well described by the long wavelength modes. Okay. In other words, if I have to describe the densities, the density distribution or density correlation in these grids, basically one number per grid, so that is my density field, I can just do it with the large scale modes of the power spectrum. Okay, the small scales don't matter. So let us say, so this density, let us say it has a very long wavelength fluctuation. It doesn't fluctuate very rapidly. So this will be the density of these grids. On top of that, there are these small scale fluctuations which will give rise to these halos. So there are these small scale fluctuations on top of this. And these are the peaks which will eventually go and form the halo. Now in this case, you see, suppose I draw some barrier which this field needs to cross to form a halo. You can see these small wavelength modes, they have an advantage. If they are sitting on top of this long wavelength mode, they don't really have to start from zero. They can just cross this much of the barrier and then they are done. Whereas if you are sitting on a trough of a long wavelength mode, that is the low density regions, then you have to do a lot of work. You have to go to, really make a big jump to reach there. So this is one way of understanding why overdensities will have more halos. And the way I did it, this is called peak background split. So there is this underlying long wavelength fluctuation. On top of that, there are these small scale fluctuations, and the peaks of, actually the combined peak is what it matters, but the peak will be mostly dominated by these small scale ones which have power. So if we trust this picture, then the problem actually becomes very simple. Then what we have to do is, we just say that Nm xz, I will write the same formula, 2 by pi rho bar by m d ln sigma m by dm, and then I write something I call nu b, e to the minus nu b square by 2, where now this nu b is nothing but delta c by delta of x divided by d plus z sigma m. This is the standard matter density. So what I have earlier, nu was delta c by d plus sigma. What I am saying is, so that meant that sigma should have enough dispersion to cross delta c. Now I am saying that you don't have to cross delta c, you can cross less if you are sitting in an overdense region. And vice versa, if delta m is negative, then you are doomed. You have to cross so much that it will become very difficult to form halos. So this is the expression for halo density as a function of the underlying density field. Okay. Now, suppose we want to simplify this, what we can do is, as I said, we basically made sure that these things are determined by the long wavelength modes, and hence at large scales, typically the density fluctuations are small. So what we can do is we can do a Taylor series expansion around delta m equal to 0. So let us do that. So then what will happen is Nm, I will write it as Nm evaluated at delta m equal to 0 plus the del Nm del delta m evaluated at delta m equal to 0 times delta m plus order delta m square. So for the moment, we will ignore the higher order terms. Let us see what happens the lowest order. The first term is nothing but Nm bar, right? If I put delta m equal to 0, then I get back the original Prayush formula. And then what you have to do is, I have to do something like del Nm, because delta m is sitting basically within nu. So I do a delta nu b and then delta nu b delta Lm. Make sure it is evaluated at delta m equal to 0 times delta m plus higher order terms. Now this derivative you can calculate just from looking at that expression. It's all given there. So if you do that, what you will end up with is, I'm just writing the final expression. There are like some steps involved. It will be Nm bar plus, okay, let me just go to the final step. It is 1 plus, so 1 is the first term. The second term is nu square minus 1 by delta C into delta M. So if I now want to write the contrast of halos, so let us put those dependencies X, M, Z. It just becomes nu square minus 1 delta C times delta M, which is also evaluated at X. So now you see the delta halo like qualitatively follows delta M, in the sense where delta M is higher, delta halo will be higher, but it is not equal. The fluctuations are not equal. In fact, they are amplified. There is one more subtlety which we have to account for, and that's slightly difficult to understand, but it happens. What happens is all these things, all these calculation of these peaks, all these barrier crossing and everything happens at the initial condition level. We have linearly extrapolated it, but everything is happening at that level. So that is what we call the Lagrangian space. Whereas in the simulations or in the real universe, you will calculate something in some volume which is happening at that redshift, at that volume. That is not happening in that volume of the initial condition. So what happens is, for a given overdensity, the volume essentially decreases. That is like, you can imagine if there is overdensity, the volume will be less compared to previously. This is the co-moving volume, so the expansion is not playing any role here. And that volume, so basically there is a Lagrangian to Eulerian correction, and that essentially change is exactly 1 plus delta. So what you have to do is you have to multiply this by 1 plus delta and then again ignore the higher order terms. So this essentially then becomes 1 plus nu square minus 1 by delta C times delta M. Often this is written as delta H xm. I'm suppressing the z because everything is happening at the same redshift as Bm times delta M x. Where Bm is known as the linear halo bias. So bias essentially tells you how different is the fluctuations in the tracer you are interested in compared to underlying matter. So you, in principle, you can calculate this bias for any tracer you are interested in. We are doing it for halos. Eventually, we can do it for galaxies, and we will do that, and for gravitational wave events. And we also make sure we write linear because everything was done in the linear approximation. Higher order terms were included. We said that delta M should be very small. So make sure these sizes of these grids or the regions you are looking at are large. So all this long wavelength mode picture is valid. Okay. So this bias basically captures how different the power spectrum will be. Power spectrum of halos or 2-point correlation of the halos would be from the underlying matter 2-point correlation function. So if I now go forward and calculate the 2-point correlation of halos, so that let us say that is x1 minus x2, and let us say I cross correlate halos of mass m1 with some mass m2. Okay, so you say that I'm looking for a cross correlation such that I found a halo of mass m1 in position x1 and a halo of mass m2 in position x2. And then I check this for all possible realization for the same x1 minus x2. This one will turn out to be, I mean, this is kind of defined as delta H at x1 m1, delta H at x2 m2. And if I put this back, put this expression here, this one will turn out to be B of m1, B of m2, psi of m, x1 minus x2. In fact, it will be mod, but I'm just not putting the mod. It will have Z dependence basically, okay, through nu. Yes. Yes. Okay. If you are interested in just halos of one mass, then it will become B square. And you can write similar expressions for power spectrum as well. Since it is easier to do it in real space because halos are in real space, I am doing it in this way. Suppose you are interested in all halos above some mass m min, let us say. Okay, so you say that I take 10 to the 10 solar mass halos. I am interested in all the halos. Above 10 to the 10 solar mass, I don't distinguish. And I want to calculate the 2-point correlation function of these halos. So now all m's will be mixed. Okay, sometimes in position 1 you will have halos of some mass, position 2 you have halos of some other mass, but they will all be above m min. In that case, this quantity, the 2-point correlation function, x1 minus x2, let us say writing just as m min, will be basically you have to average over all halos of the dn dm1, then again m min to infinity, dm2 dn dm2 psi halo x1 minus x2 m1 m2, and then you have to ensure that you take the average properly. So you have to make sure you count the number of halos. Okay. So what you are saying is at point m1, at point x1, I have halo of mass m1. At point x2, I have halo of mass m2. And in each of these cases, because I have allowed all halos to be there above m min, so m1 can go from m min to infinity, m2 can also go from m min to infinity. However, not all masses are equally probable. So I have to make sure that I count the number, I weigh it by the number of halos of that mass. Okay, so that, I mean, very clearly the high mass halos will be exponentially suppressed. So even if I do all calculate, take into account all the masses above m min, very high mass halos will be anyway not showing up. So that is accounted for by this integral. And if we put this one back, what I will have is, so this xi halo will be bm1 times bm2 times xi matter. And xi matter does not depend on the mass of the halo, so that will just come out. So I will have an integral which will be m min to infinity dm1 mass function times bm1, and then m min to infinity dn dm2 dm2 dn dm2 bm2 divided by whatever was there in the denominator. I am not writing again, psi m x1 minus x2. So this will be written as b square above m min times psi m x1 minus x2, where b greater than some m min is nothing but the quantity which is there, m min to infinity dm dn dm bm by m into infinity dm dn dm. So this will be the bias if I average over the whole population. So we now know how to calculate the correlation function for halos. But let us see what does this bias or this correlation function tell us. So it is here. So the bias is this quantity, right? So as mass, let us say, increases, sigma m, what happens to sigma m when mass increases? Does it increase or decrease? Decrease. If sigma m decreases, then what happens to nu? How was nu related to sigma m? So sigma m was in the denominator, right? So nu will increase. So just by looking at this, it's clear that when mass increases, the fluctuations increase, and hence, so basically the bias fluctuations increases, the bias increases, and hence the 2-point correlation function will also increase. That is telling you that high mass halos are more clustered than low mass halos. Okay, so if I go to your simulation or any sample, you just divide it in some way. Take only the high mass halo and take only the low mass halo, and calculate their correlation functions or power spectra separately. What you will find is, firstly, both of them will follow the underlying matter distribution, but with some offset. That is the bias. And low mass halos will have lower bias, so they will be probably closer to the matter power spectrum. High mass halos will have higher bias. So then the picture you need to have is this. We also said that high mass halos are rare. They are not very easy to form because you have to really cross. I mean, they don't find it very easy to cross the barrier. Sigma is too small for them. So in the universe, for a long time, you may not have high mass halos. But once they start forming, if you form a halo here, it's very likely you will form a few more halos nearby. And that is why the clustering shows up. I mean, becomes higher, I mean, compared to the underlying matter. So they will probably form in some high density regions, but once a few form, there will be more forming around that region. And vice versa, regions which are deprived of halos will tend to remain more deprived of halos. So that is the picture one needs to have. Now, of course, this was a simple calculation, remember? So beyond the linear regime, you can have more complicated forms of bias. Also, more importantly, this bias can pick up scale dependence. In the sense, currently the way I have written, this psi as a function of x, psi halo as a function of x, the x dependence is only at the matter correlation function level. This one is just a kind of number at that redshift for a given mass range. A full calculation, for a more detailed calculation, this one can also pick up scale dependence. So it may not be exactly following the 2-point correlation function. However, at large scales, this is a good approximation. And that is what you will often see in your simulations as well as in observations. So that was all about clustering of halos. Yeah. Just one more thing, sometimes we may be interested in calculating the cross correlation function. So maybe we will be interested in calculating something like delta H at x1 m, I mean, and delta m at x2. Okay, we will call it psi halo hm x1 minus x2. And that will turn out to be B of m psi m x1 minus x2. So 2-point correlation of halos, like correlation of halos with halos, will pick up 2 factors of B. If you do cross correlation with the underlying matter, it will pick up 1 factor of B. And if you do matter with matter, there is no bias, obviously. So that was all about clustering of halos. So now we have seen what are the conditions in which halos form, this crossing of threshold, so on. Then what are the distribution, the mass distribution of halos. And now we have also seen what are the clustering properties of these halos. And all of these go as inputs to various cosmological observations when you do modeling of these observations. So then the next step would be to see what happens inside these halos, because observationally we don't see these halos, okay? They are dark. I mean, they are mostly made up of dark matter. What we see are galaxies, in particular light from galaxies. So most likely we will be seeing stars. You may see some active galactic nuclei as well. But for simplicity, let us say we are observing, I mean, most of these galaxy surveys are basically receiving starlight. And that is what is allowing you to trace all these large scale structures. So many of these observational maps you see are basically galaxies. And these dark matter halos are not galaxies. Galaxies form inside dark matter halos. So then how does this galaxy formation happen? Now this is an extremely complex and nonlinear problem where you have to track basically gas. And till now, we have been doing many things almost analytically. We are writing down equations and trying to get insights. The moment you come here, this becomes more and more difficult. You can probably use some idea about fluid dynamics here, but beyond a point, it becomes extremely difficult. So most of the galaxy formation studies are again done using either simulations, or even if they are analytical models, you have to solve them numerically. You can at best write down the differential equations, and there could be many coupled differential equations, and you solve them and try to see what happens. There is very little you can do analytically the moment galaxy formation kicks in. So now we will become a bit qualitative and try to see what happens to the gas inside the halo. So a halo, let us say, has formed, and we were mostly talking about spherical halos. These are some mass m and some radius r. So as we said, the potential is essentially dominated by dark matter. So once the halo forms, as the halo was forming, the baryons were essentially, the gas were following the dark matter. So once the halo forms, the gas is also trapped inside because there is so much potential there, the gas cannot escape. Now if the gas is trapped inside and you have reached some kind of an equilibrium, what will happen is the gas will pick up kinetic energy. The gas particles will pick up kinetic energy, and that kinetic energy will be driven by the potential of the halo. And if you now try to calculate the temperature of the gas, that will be typically the virial temperature of the halo, which is Gm by R virial, the virial radius at which the halo collapses. Okay, so KT will be this. And we will assume that the gas is mostly consisting of hydrogen. I mean, even maybe a bit, even if there are other molecules, I mean, mass of the nuclei, I mean, the mass of the proton is the underlying like unit with which we can work. Now, if you look at this temperature for typical halos, this temperature, for example, for 10 to the 8 solar mass halos, this T virial will be 10 to the 4 Kelvin. We have also seen that the typical density will be few hundred. And I mean, within that halo, the gas will basically settle down with essentially this kind of numbers. Now, neither this density nor the temperature is suitable to start forming stars, in particular the density, okay? Cosmological densities are very, very, very small. Okay? And this, of course, is amplified by a couple of orders of magnitude, but it is nowhere close to the stellar density, which we need to ignite nuclear reactions. So if the gas was just sitting here in that halo, nothing will happen. The gas will just be there. So no star formation, no halo formation. So somehow you have to make this gas more dense, okay? You have to condense this gas. To condense this gas, you have to cool it because the temperature is what is giving rise to the pressure and it is not able to come together, okay? So whatever if you want to form stars, the first thing you need to do is cooling. Now there are various ways of cooling, but the one which plays a role in star formation is something called collisional cooling or cooling followed by collisional excitation. So what would have happened is, for simplicity, let us assume that the gas is made up of hydrogen entirely. Then what you need to do is, let us say the hydrogen is in the ground state, the electron is in the ground state of the hydrogen atom. Somehow, through some collision or through some other process, if you can put the electron to a higher excited state, n equal to 2, 3, wherever you want, it will go there, and when it comes down back to the ground state, it will emit a photon, okay? It will emit radiation. If that radiation escapes, okay, can come out from this halo, what will happen is effectively you have lost energy. So you started with something in the ground state, it went up, came back to the ground state, but in the middle you have basically given up a photon. So essentially, on average, the energy of the system will go down. So this is one way of cooling, okay? So this is basically collisional cooling. You can also do through ionization. I mean, you can ionize the electron, and when it recombines, it will also lead to cooling. Yeah.
If I just calculate the heat loss just due to thermal radiation, the sigma T to the 4 is very small as compared to the cooling.
What do you mean sigma T to the 4? How will that cool? What will take away that energy?
Radiation.
So how will radiation take away that energy? How will the radiation take away energy? I put some hydrogen in ground state. Now you tell me, how will the energy come out? So all these black body radiations you are thinking about, anything, there has to be a microscopic interaction happening inside. Okay, so it could be some atoms exciting and coming down. Without that, radiation won't come out. So sigma T to the power 4, we think of black body, and the black body is radiating because something is happening inside. Otherwise, no. So often sigma in the astrophysics, sigma T to the power 4 is used in stars. Stars are radiating. I mean, not because of collision, but because of whatever is happening inside the star. So yeah, so now what you have asked is very interesting. Now suppose I ask that, let us say I am in a smaller halo. Okay, so smaller halos has less temperature. So let us take a thought experiment. Okay, let us say I am taking a 10 to the 6 to 10 to the 7 solar mass halos. And for example, the temperature is 10 to the 3K. I don't remember exactly what this would correspond, but that will be less than 10 to the 4K. So let us say it is 1000 Kelvin. So can you tell me at 1000 Kelvin, if I have hydrogen atom, in the electron, in which state it is likely to be? Okay, so for that you need to know the typical energy difference between the ground state and the first excited state. That is of the order of 10 electron volts, right? Ionization is 13.6 electron volts, that is 10.2, and you can calculate that temperature will turn out to be something like 10 to the 4K of that order. Okay. Now, suppose the temperature of the gas is 10 to the 3K, where will the hydrogen be? Mostly in the ground state. This is the typical kinetic energy they have. So even if they collide, it will be very difficult to excite the electron to the higher excited state. And if you cannot do that, you won't be able to cool. So now it's a kind of paradoxical situation. If you start with a halo, which has virial temperature less than 10 to the 4K, you won't be able to cool. In fact, the gas just stays put there. Okay, there is no cooling, no star formation. if only hydrogen is present. Okay. If there are other elements, they can give you other lines. For example, metals, higher order elements, they have lines which are more closely separated because of their complex structure, all these rotational and vibrational levels. They will help in cooling. So can hydrogen molecules, H2 molecules. But with only atomic hydrogen, these halos will never cool. Okay. But they have temperature 10 to the 3K. But they are just sitting there. No radiation is going to come out. So you see the first condition already. If the gas is made up of hydrogen, you need it to be above some value to start the cooling. And cooling is the first kind of necessary choice. And when, I mean, so people who do first stars, this is a big problem because in the early universe, when no stars have formed, there is no metal pollution. Okay, so there is no carbon, no oxygen, no higher order elements. It's all hydrogen and helium. And it's not very easy to cool the gas through these only. You have to really hit this kind of halos. And as I was saying, small mass halos are easy to form, but they may not form stars. So at early times, the only way you can form stars and smaller mass halos is if you can form H2 molecules somehow. So there is a lot of controversy in the literature about how efficient H2 molecules formation are, but if you can form, this can go down significantly. I mean, you can then go to about a few hundred Kelvin and then form stars. Okay, these are usually called mini halos. But let us not go into the details. Let us understand the physical, the principle that the halo mass needs to be above some threshold for them to start forming stars. For cooling, I mean, we haven't come to start. Now, once you cool, then something interesting happens. Okay. What happens is, as we were saying, so there is this gravity which is trying to collapse the gas, and pressure is resisting. And pressure often is characterized either by temperature or the sound speed. Okay, all of them are related to each other. Now, this competition between gravity and pressure is, in our earlier lectures, is captured in a quantity called gene scale. The same gene scale appear here, but in this case, it is easier to work with mass. Mass is nothing but you convert that scale into a volume and then to a mass and take the density of a typical halo. Okay. So that gene scale will turn out to be, I'm just writing the scalings, the actual relations are not important. Omega to the power minus half, t to the 3 by 2. So if you go back to the relation, I mean the expression we wrote for xj or xb or something we wrote, you can from there at least understand these scalings. Okay, that is not difficult. So this is the gene's mass. So what it tells you is that if the mass is above mj, it can collapse. If it is less than mj, then pressure support wins. Now, initially, the gene's mass is high enough that this collapse does not happen. And then T goes down. Okay, T goes down because this radiation comes out. Now, there is another subtlety we have to keep in mind. It is not like the atom goes up, comes down, a photon is produced. That doesn't mean the photon will come out of the system. The system has to be optically thin, meaning the probability of absorbing that photon has to be quite small. So if the density becomes too high, then that photon will itself get absorbed by the material there. Okay, that same hydrogen atom may absorb the photon. Then you are stuck. Okay, then again cooling becomes difficult. So optically thin, what happens is the temperature tends to go down initially. So the mj will go down. So the mass which was then pressure supported, now because the mj has gone down, that mass has become larger than mj. So it can start to collapse. Okay, it will become a bit more dense. I will come to that. So for the moment, let us assume that the density is small enough so that the opacity is small. Okay, so as you start condensing, clearly the density will go up and something else will happen. So what happens is, as the cloud collapses, basically, as the cloud collapses, something else happens. Now rho will go up. Okay, if the rho goes up, then mj can again go up. So that is the competition you have to deal with. So you have to cool fast enough that this mj keeps on kind of decreasing. Okay. So here basically the idea is that this constantly kind of radiates, adjusts itself, and the mj keeps on decreasing and it starts collapsing. What happens is, initially you may have a huge cloud. So at 10 to the 8 solar mass halo, the baryons can be of the order of 10 to the 7 solar mass there. Okay. This is a huge cloud, but as the Jeans mass decreases, what happens is this gas starts to fragment. And depending on what the Jeans mass is, you will form fragments of that mass. So basically you start with this huge gas cloud, then it starts to fragment and then fragment further and so on. And the whole process basically leads to something where rho is high. Now, as one of you asked, this cannot be a runaway process. At some point it stops. It stops when rho becomes so high that this optically thin goes to optically thick. Then the radiation cannot escape, and then the dependencies change inside. And now, if you try to condense more, the gene scale, in fact, it tends to become large. And that is where the problem, that is where this whole process stops. What we can do is, one can do this order of magnitude calculations and try to see where this process stops. And this was done like decades back by various people. And interestingly, the mass scale where this process stops, you will find that this is somewhere between 0.1 to 1 solar mass. Okay, a typical mass of stars. So this indirectly tells you why a typical stellar mass is like the mass of our sun. Or at least this is the kind of minimum mass of stars you can have. You really cannot have masses much smaller than this. The process, unfortunately, neither is this simple, nor it stops here. What happens is, by this time, the gas has picked up various things. So there are effects of turbulence. The medium becomes turbulent. What we haven't at all considered is rotation and things like shear. And there is also an effect of magnetic field, which makes things much more interesting. So even after this, what happens is, there is this, you can think of this as a protostar. It will still try to keep on accreting material, but that will also will stop at some point because of feedback effects. But all those details, we can forget. But what it means is that it has to go through a series of complex processes for it to form stars. And not all the stars will be of same mass. Okay, it will depend on the stochasticity of this process. Okay, some will condense to a smaller mass, some higher mass, and you will get a distribution of mass at the end. Yeah.
Calculate of the values that ensure that the hydrogen atoms are neutral. They just but then where is this magnetic field coming?
No. Okay. Magnetic field is basically everywhere in the universe. So magnetic field is magnetic field. But as, I mean, so see, if you have halos, I said 10 to the 8 solar mass. If you just take halos larger than this, the temperature will be high enough to make the gas kind of non-trivial. Okay. So there will be, I mean, so the magnetic field is set up because of various other processes, maybe because of the fluids, some parts of the fluids becoming ionized. So if you look at our galaxy, there are parts of the interstellar medium which are very highly ionized, and then a part of medium which is very neutral, okay? And then there are parts which are warm, there are parts which are cold. So it is a very complex process which sets up all these things, and all these things will essentially set up the distribution of masses in stars.
Our galaxy stars have already formed. First star.
Yes.
So in that case, I'm not able to see it. So you are saying that it comes from the other heavier mass.
I mean, T to the 4k, you will have ionization. That is not a problem. I mean, see, 10 to the energy difference between n equal to 1 and n equal to 2 level and n equal to 1 and n equal to infinity level are very close. One is 13.6 and one is 10. This is a typical problem again in astrophysics, that you cannot, suppose you want to create a situation where you want to keep the hydrogen atom at higher excited states but not ionize. It's very difficult. Okay, so this process often ends up in ionizing, I mean, some probability of ionizing the hydrogen atom. So that is not a problem. So magnetic fields playing a role is not a problem. The problem is to really figure out what role it plays, because you cannot do it using simple equations. Okay. Yeah. That is radiation pressure, right? No, that is high mass end, right? Where the radiation is so high, I mean, that it basically you cannot sustain the star, right? No, I'm saying the other thing. Why Jupiter cannot be. Otherwise, the hydrogen will not start falling into the. I think that we can put a bound on that, right? The prototype only be planet. No, that is not correct. Firstly, so I will tell you why. So this 0.1 to 1 solar mass I put is for a medium which consists of metals like our galaxy. Suppose I was forming stars at very early redshifts where there was no metals, it was only hydrogen and helium. This number will turn out to be 10 to 100 solar mass. Why? Because the cooling is not efficient and you cannot go down too much. You get pressure supported very early. That is why we believe that the first stars are much heavier than the stars we see around us today. So these are what are known as population 3 stars. So it is really this cooling process which sets this scale. Okay. Now let us say you have formed this star. You have gone through this very complicated process, very difficult to deal with. Now, once you do that, what you will be interested in is a quantity called star formation rate. So let me come back this side. And that is a quantity which is very widely used in cosmology. So star formation rate. SFR. It is basically in a galaxy the rate at which stars are formed, basically. So m star dot. So the units will be mass per time. So typically we measure it in units of solar mass per year. Often this is also written as psi. Particularly in gravitational wave literature, you will see this psi. Now, suppose I have a halo. It goes through all these processes and forms stars. Clearly, it will depend on so many things. It will depend on the whatever, the gas density. More importantly, it will depend on the metallicity. As I've been constantly saying, those will set up the cooling channels. And who knows, it will depend on the environment and so on. So if I have to, for a given halo, if I have to model this, it can be quite complicated. But let us, for the moment, make a very simplifying assumption that psi depends just on the halo mass and redshift. What we are implicitly assuming is, of course, psi will depend on metallicity and other things. But on a given redshift, these metallicity or any other thing are also given by the halo mass. In other words, if you have 10 to the 8 solar mass halos at redshift 12, all of them will have the same metallicity, same cooling, and hence the same star formation rate. This is an assumption. This is not true. And I will tell you later in this lecture, if I have time, what happens if we try to make it more complicated. So let us say this is my star formation rate in a halo. And one very typical model which is used is, you say, okay, you say it is proportional to the mass of the halo, but not really the mass of the halo. The mass of baryons is inside the halo. And then you say only a fraction goes into star, and the star formation happens at a time scale which is T star. So this is one typical model of star formation rate. And then what you have to do is you have to ask how to model these quantities. It will depend on how sophisticated your model is. Or what you will do is you will treat this as a free parameter and try to fix it by comparing with observations. We have also implicitly assumed in this thing that there is just one galaxy per halo. And I will talk about this assumption very soon. Okay. So there is this halo, all this cooling and everything happens, a galaxy forms, galaxy is forming stars at this rate. If you want, you can make this model, but that is not important. What is often used is this quantity, the global star formation history, that is, in our universe, what is the star formation rate per unit volume? That will be basically dm psi mz dn. So our halo mass function is back again. So what I have to do is I have to count the number of halos. In each halo, how much stars are forming, what is the star formation rate, integrate over all of them. And you can convince yourself that this is indeed mass per unit time per unit volume. And often in literature, this is something which is like used. People would have taken a wide range of observations over a wide range of redshifts and tried to compute this, and there will be a plot given. A very popular plot is that given by Maddow and Dickinson, which many people use. But even here, there are subtleties which you need to be worried about. Firstly, now star formation rate is not a directly observable quantity. We look at galaxies, we get light, okay? I mean, we don't see stars forming. Like I wait for 1 year and it's not like I see more stars have formed or something like that. What you get is the luminosity in some wavelength, okay? Typically in some UV wavelength, in the rest frame of the galaxy which we are interested in. It could be some people use 1500 angstrom, 1250. These are some typical numbers. It depends on the experiment one is interested in, but the exact value is not important. This luminosity is what one is looking for. And that luminosity of a galaxy is luminosity of each star convolved with the mass function of the stars, okay, not the halos. I mean, how many stars of each mass you have formed. Now, this luminosity, if you give the, for example, metallicity IMF, so this is a notation for metallicity, IMF, age, if you specify all these quantities, there are calculations called population synthesis models. And there are publicly available versions of them, which will give you this luminosity. It will give you many properties, many observable properties of that quantity, of that stellar population. So using that, you can calculate the luminosity, and that is directly observable. And then you make like a relation between this luminosity and star formation rate. So you observe the luminosity, you make a connection between luminosity and star formation rate, which itself depends on all these quantities, and then only you can make this plot, calculate this quantity. But let us say that fine. I mean, if luminosity is the observable quantity, let us for the time being, why don't we work with luminosity? So see, this model is something I just wrote. So I can write the same for luminosity. No, I mean, I will just say that luminosity is a function of halo mass and Z. And maybe I will make a model for that. So then you suppose you have some model, okay, you have come up with some model. Given a halo mass, it tells you what the luminosity would be. Then you can try to compute observable, which is the luminosity function. Just like we did mass function, you can do luminosity function. It is basically the number of galaxies within a per luminosity range within some L and L plus DL. Usually written as phi L. But that phi L is directly related to D and dm if you have a one-to-one relation between L and M, which is your model. So for every M, you have found a way to calculate L. And then you can actually go and compare with observations, because D and dm you know how to calculate. Either you use Prayush, very unlikely, you use some more complicated fitting form, or you run a simulation and take the D and dm from that. So you have all these halos in your simulation. Go and like paint luminosity in each of the halos if you have a model there. And that will give you a luminosity map, like there are all these galaxies sitting with luminosities. To the first order, you calculate the luminosity function, bin in luminosity and find out how many galaxies are there per unit volume. Simple. And this is observable. Now, in the first approximation, you will say that let us take luminosity to be just proportional to M. Proportionality constant is a constant, at least at one redshift, it is just some number. So then what will happen is this luminosity function will be like a scaled version of the halo mass function. It will have the same kind of shape, power law followed by exponential suppression. So then your model, you will get something which will look like this. And then you will say that, okay, let me try to like adjust this constant so that I can match the observations. Now you can adjust this constant, but what will happen is this shape will remain the same as long as this is constant. So you cannot do any arbitrary things. It will turn out that the data will look something like this. Okay, let me try to draw it a bit differently. Let me try to draw the data first. And your model would be very much like this. So what happens is, even if you try to adjust this, it will be very difficult to match the data. So this will go less prominently. So you can shift the curve this way, that way, using this scaling. It will never come and sit on the data. So the best you may be able to do is something which looks like this. It comes here and then falls like this. So you will be able to match the data around this point. You will neither be able to match the data at the faint luminosity end, neither at the large luminosity end. That was the first indication that there is something happening at both the ends. And people then came up with the concept of feedback. Basically, what happens is L is not proportional to M. Rather, if you try to plot L versus M with M, if you try to plot L by M versus M, I mean, initially you wanted it to be a constant. It will turn out to be something like this, because you want this to go down in both the sides. And our understanding is this part, low mass end, is happening because of something called supernova feedback. And this part is happening because of something called AGN feedback. So there are these feedback effects which are not allowing the gas to cool efficiently and form stars. I can discuss this in more detail if somebody is interested, but for the timing, let us leave it at this. So this is the first indication where one could use cosmological observations without really worrying about the galaxy formation physics to start with. Try to model it and then infer some galaxy formation physics from the observations. You see what the observations tell you. The hope is that at some point, once new avenues open, which could be gravitational wave sources, we could do something like this as well. It will tell us about what kind of channels is better for gravitational waves, I mean, binaries to merge, and what kind of halo masses are not good for binaries to form, and so on. But the story does not end here. Okay. Yeah. Yes. So this is at redshift, low redshift. These are, for example, coming from SDSS data. Okay, so we don't have this level of data at high redshifts to actually do all these. Yeah. But what you are saying is correct. Supernova comes from stars. AGN also, it is happening because of the central black hole, and it's not easy to have those things very early. Yeah. Now, for the fast stars, it could be completely different. And we see these things change with redshift. But what we can do is, I can play this game if the data is available at every redshift and try to infer this. Except the story, unfortunately, is way more complicated than this. And now that is our next thing. So now what we can do is, suppose now I have painted all my halos with some luminosity. Okay. Now there is no other freedom. So all the halos have some luminosity. I'm very happy that it matches the luminosity function. Almost by construction, I have chosen that relation so that it matches the luminosity function. Now what do we do? By the way, choosing this to match the observation is often called abundance matching. There is a formal name. You can do it very rigorously, but this is a jargon which you may want to keep in mind. Now you say, I have all my galaxies sitting in halos with luminosity. Now I will find the clustering of these galaxies. So what you can do is, you say that I will choose only galaxies which are above some limit, because this may happen in the observation, or let me put this limit, or I can put between L-min and L-max also. And then I will do the clustering. What would be interesting to find is what is B greater than L-min, and this is all happening at some fixed redshift. And that will be given by L-min to infinity dl bias of halo of mass m, which is giving you this luminosity, and phi of L, and then you normalize by L-min to infinity dl phi L. So this gives you the clustering amplitude, right? You multiply this by the matter correlation function, that will give you what is the correlation. And again, if somebody remembers the slides I showed in the first lecture, people have calculated this correlation for galaxies as a function of luminosities. They have divided the galaxies into luminosity bins and calculated the clustering. Okay, so it would be like between some two luminosity bins. Now, if L kind of increases with M, then we know that high mass halos have higher bias. So then that immediately tells you that high luminosity galaxies will have higher clustering or higher bias. In observations, you see that. Okay, brighter galaxies have higher bias. So qualitatively, this model will do fine. But when you try to actually match quantitatively, because you have lost all the freedom now, you have to make sure it goes and sits on the plots for correlation function. It does not, okay? So qualitatively it works well, but quantitatively you will find it to be very difficult. And then, of course, because the data is so rich, people could do it at lower redshift. You realize that all these things you decided that one galaxy per halo, this does not work. Okay, and then you have to worry about a halo having multiple galaxies. There could be central galaxies, there could be satellites going around them, and there could be halos which may not have galaxies. Okay, so you have to characterize everything by a probability distribution of number of galaxies in a halo of mass m with some luminosity L. This is known as halo occupation distribution, or HOD. And this is the level of modeling you actually need to match the data you have at low redshift. Now you see, so you can learn a lot from this 1-point statistics, which is the luminosity function. Okay, but the moment you put in 2-point statistics, I mean, your understanding has to be much better at that level. Okay, simple models may not work. Okay, simple models will work only if the universe is really simple. Okay, if the universe is more complicated, some of these complications need to go into these models. So this I'm choosing as a kind of example at low redshift what happened, and this is the idea which can be. So this is being tried at high redshifts also. People are trying to replicate this at high redshifts as more and more data are coming into the fore, so that we understand how does galaxies populate the halos. So you can then, I mean, from this discussion, it is clear you can take two approaches. One is you can model all these complicated physics, forward model them, and predict what kind of galaxies will be formed inside halos and try to match with observations. So there are models of galaxy formation. Okay, there are semi-analytical models of galaxy formation, and many of these famous simulations also try to do that. Okay, all these Illustris and other simulations have some mechanism put in to paint the halos with galaxies, but they solve some basic equations there. That is one approach. The other approach is you say that I will keep the model not simple but parametric. Okay, so I will just parameterize. So this probability distribution I will parameterize by some parameters. And then I will try to fit all the observations and infer those parameters. And from there I will learn what it is, that how the luminosity changes with mass, what kind of halos host many galaxies, what kind of halos don't host any galaxy, and all these questions can then be answered. Then I only talked about luminosity. You can play the same game with what are known as color. Okay, you can define color of the galaxies based on their luminosities at different bands, and you can again play the same game. So all these things are being done in cosmology, essentially. Now, whatever time is left, let us take the next step, which is to relate this to the theme of this school. That is, suppose I want to do the same thing for gravitational wave events. Now, how do I do that? So again, for all of this lecture, our simple assumption will be that there is just one galaxy in a halo, and everything, all property of that galaxy is determined by the halo mass and nothing else. So this halo of mass m has formed stars with some star formation rate, and these stars have also formed in some, so let us not go into the initial mass function. There is, so only a fraction of stars are massive enough to form the compact objects which we are interested in for gravitational wave events. This could be larger than 7 to 8 solar mass typically. Okay, their end stages is something which we would be interested in. Now, not all of them will go into, only a fraction will go into binaries. And then out of that, only a fraction will merge in a reasonable amount of time. Okay, so it's not like all stars which are forming will all go and start giving you gravitational wave events. So all these things you have to understand. And for that, this you need to understand what is the mass distribution of stars, what fraction of stars are massive. So as I said, at early times, when the metallicity is small, it is easier to form massive stars, and vice versa. So let us take this quantity dn merge dmc dm star. So this I am calling number of mergers. These are mergers of these compact objects which will give you gravitational wave events. Don't confuse it with the merger of halos which we are talking about in the morning. Per chirp mass range, per unit stellar mass, at redshift z. Okay, so there is, so this is all happening inside a halo of mass m at redshift z. So let us say this is the number of mergers per unit chirp mass range per unit stellar mass. So what will happen is a fraction will be in binaries, and then if they go to gravitational wave events, you will have a distribution of chirp masses which will depend on the masses of the progenitors. Okay. And I put a per unit stellar mass here because the assumption here is the more stars you form, the more such events will be present. For the moment, let us ignore the delay time. In the sense, let us assume that as soon as the star is formed, if possible, a gravitational wave event can go on. I will put in the delay time later. Let us keep it simple for the time being, and we will make things complicated as we go along. So what I'm trying to do is, starting from this, I'm trying to build what is actually observed in the detector. So since we had seen psi is m star dot, so what I can do is I can multiply this quantity by psi and say that dn merge mz dmc dm star is the number of, again, mergers per chirp mass range per unit time. So it was per unit stellar mass, but now I have multiplied it by the star formation rate, which is stellar mass per unit time. So this has become number of merger per chirp mass range per unit time, all happening in one halo of mass m. And again, let me emphasize that to model this, you may need to understand all these quantities, okay? What fraction of it has gone into massive stars, how many are the binaries, and so on. Now, if you have followed what we were doing for the galaxy luminosity function, the next step is to integrate over all halos. So this is for one halo of mass m. So now you say that I will integrate over all halos. So let us say, and for each halo, I have basically found out what is the star formation rate. Okay, that was the original idea. In this case, we went to luminosity, but let us say I have a way to calculate star formation rate for each halo. So d psi times this quantity dn merge mz by dmc dm star times our friend dn dm, which is a function of mz, our mass function, and then dm d psi. This basically will be number of mergers per chirp mass per unit time. And now let me make something in the source frame, which was true here also. Per co-moving volume. So that was merger per DMC per unit time. But so this is also mergers per DMC per unit time. That was for one halo. But this I have now multiplied by all halos within that mass range. Now this has become number of merger per chirp mass range per unit time. But remember, in the source frame, meaning where this is happening, per co-moving volume. The co-moving volume has come because of this d and dm. Okay. Now the next thing I want to do is the unit time in source frame. I want to convert it into unit time in our frame, observer frame. That will be related by cosmological time dilation. So there will be an extra 1 plus z factor. Second is we are interested in events coming from a redshift interval between z and z plus dz. So what I will do is I will convert this co-moving volume into a redshift interval. So how do I do that? So that will be done using two quantities. One is, so converting redshift into volume is something we did earlier, redshift range and volume, is that if I am interested in all the events coming from a particular redshift range, that redshift range is sitting at some distance here. So this is that distance, chi or whatever, and this is that thickness, delta z or delta chi, whatever you want to say. And I'm saying I'm interested in all the events happening here. So what I need to do is I need to calculate the relation between co-moving volume and redshift, and that will essentially be 4 pi chi square z c, I mean there is basically this is d chi dz. If you remember when we were writing relations between this volume solid angle and Cartesian coordinates, this is the kind of relation you would have used. Except there you had a d omega. Now you are saying I don't care about the omega. Let it come from any side it wants to come. So this is 4 pi chi square z, and d chi dz is just c by hz. So this is how I convert per co-moving volume to per redshift interval, and then I say time dilation. There is an extra factor of 1 plus z. So then I end up with a relation which is 1 by 1 plus z dvc dz. All of them are now given by z or cosmological parameters, and then this dm d psi, and that d psi basically tells me it is essentially a dm integral psi, which is a function of mz, dn merge, which hopefully I will be able to model someday, mz by dmc dm star times dn mz dm. So this is number of mergers. It's essentially same per DMC per unit time, but now in observer frame. And per co-moving volume, instead of that, per dz. So let me write this in a form, dn merge per dmc per dt in observer frame per dz. And this is what we hope that the detectors will give us. Okay, number of events within some time. It will also tell us what the chirp mass is, so we can bin it in chirp mass range. And hopefully we will know what redshift it is coming from, so we will have the redshift interval as well. Okay, so this is something which we are after. And that is given by all these complications. Okay, and I still have to make one more complication in. Yeah. It could be. No, chirp mass will be given by the whatever, the combination of the two progenitor masses, right? What m1, m2 to the power, what, 3 by 5, I thought.
Yeah, so there's a source frame and there's a detector frame.
Yes, so fine. So this is fine. So this we have probably already corrected for from the beginning. Yeah, correct. You are right. There are geometric factors there. Correct. True. So that, let us say, has already been corrected because we started with some redshift z. So this is the observed, whatever, measured chirp mass. Or else you have to take these observations and correct to this one. Since this is just a geometric factor, that is easier to deal with. It does not depend on my star formation history and other things. Okay. This is for all galaxies in that redshift. Yes, so I'm saying this is coming from all delta D, all some dz. But then this is, I mean, suppose you say that no, I want all the events between redshift 1.5 and 3.5. You just integrate this, multiply by dz and integrate this. This is more basic. You can make it more like, depending on, you may end up seeing that in a narrow redshift range, there are so few events that there you cannot do any statistics with that. So then you may have to integrate. Now there are various complications which we have to add, and the most crucial of that is the delay time. Now the delay time happens because you will form stars, but they are not immediately going to go and give you the gravitational wave events. And there are mainly three contributions. One is the lifetime of the star, age of the star. So the star will live for some time till it actually collapses and gives you all the compact object. But we are talking about massive stars, so they could be somewhere of the order of 10 to the 7 years for massive stars. 10 solar mass stars. I think 10 solar mass is like 30 million years, something like that. So this is considerable, but maybe when you compare to the age of the universe, not that significant. There is another phase which I am not going into too much details, is the so-called common envelope phase. Okay, so this star dies, and then, as I said, only some fraction of them will end up in a binary. So what will happen is, if there is a binary companion, one of the star may expand, engulf it, basically, and within that common envelope, these stars may kind of rotate around each other and then lose energy. The thing is, this may help in actually forming a tight binary system, which is good for gravitational wave events. The thing is, this part also is not very long. It is 10 to the 4 to 10 to the 5 years. So this is almost instantaneous as far as cosmology is concerned. The thing is this merger time scale. And this can be quite long. This can be, so, I mean, just formation of this tight binary to actually merge, actually them merging and giving you the gravitational wave event. This can easily be somewhere around 10 to the 9 years, a billion years. It depends on the mass of the progenitors or the components, and also how tight the orbit is. If the orbit is very tight, they can actually merge very quick. So that could be that could be much less, 10 to the 7 to 10 to the 8 years, but it can easily go to a billion years. And this is an issue because, for example, the age of our universe at redshift 6 is billion years. So it is almost like, if this is indeed the typical time scale, then you won't see any merger before redshift 6, unless some astrophysical events, there are some astrophysical processes, or maybe the tight binaries are quite common that this is much less than billion years. So this is something to keep in mind. So if we do that, then what you have to do is, the event, let us say, has originated from redshift Z, but the galaxy has formed at redshift Z form. So what it means is, the age between TZ and age between Z and ZF is tau d. This is the delay time. And typically this delay time is characterized by a delay time distribution. So we really don't know what the delay time is. Maybe they have some spread. And on top of that, the delay time, if it depends on any of the processes which we were talking about, then yeah, it makes things way more complicated, but also interesting. And what then happens is, so basically this relation gives you an implicit relation between ZF in terms of Z and tau d. So if somebody gives you Z and tau d, you can calculate ZF from this implicit relation. So then our observable, the relation will change a bit. So dn merge divided by dt observed dmc dz will be 1 by 1 plus z dvc dz d tau d. So you have to integrate over all possible delay times whatever we had dm, but now psi will be calculated at zf, okay, not at z. This is happening at z. The merger has happened at redshift z, but it is related to psi at zf, where zf can be calculated from whatever tau d you are looking at here and the redshift you are interested in. dn merge. Now dn merge will depend on both z and zf, okay, because the merger timescale has gone in. So times dn mzf dm. So halo mass function at some early time z. Remember, this is still an extremely simple model, because we have said this, everything is given by halo mass, there is just one galaxy per halo. But even with that, you can see it can be quite intimidating to deal with. And the crucial thing here is to find a way to calculate this quantity and this quantity. Hope is that psi, we can probably try to fix it from other observations, hopefully. And then the next hope is if these observations become like abundant. I mean, you have them of a lot of events across a wide redshift range, then hopefully you can bin it in different properties of these mergers, for example, chart mass. And then if you have this model which depends on the chart mass, probably you can find a relation between what kind of halos are more likely to form something which has a chart mass between some range. Or it may not be very simple. Okay, maybe there is no obvious relation. Maybe this tau d plays a spoil sport. None of these things we know as of now. But this is the approach where we are saying that we will parameterize everything, all these unknowns, using some parameters. And if observations come, we will be able to construct them. Okay. So I'm late, I know, but let me just complete the last part, because there's no point in leaving that. Suppose now you are interested in clustering, okay, the next stage. This is just a globally average, like numbers. Suppose you want to do clustering, then what you have to do is you have to basically relate it to the bias of the halos. So for that, what you do is you don't integrate over this mass. So what you say is, I will calculate dn merge dt, everything remains same, but I don't integrate over halo mass. So this is basically, I'm just writing it again, 1 plus z dvc dz d tau d e tau d. I'm not integrating, so it is psi nz dn merge dmc dm star and dn. So this is the number of events coming from halos of mass m. Okay. And if I now want to do the clustering, so I'm just removing this part. I don't want to walk back again there. So suppose I have observed some events, then the gravitational wave clustering for events coming from redshift Z will be dm b, which can be function of m and z. This quantity dn merge dt observe dmc dz dm by this normalization dm. Yeah, I have written probably. So this is the bias of gravitational wave events, and it has it has all this information hidden kind of there. So the hope is someday we will be able to measure this as well. Fine, let me stop here. There are various things to discuss here as well, but maybe I can do it tomorrow at the beginning and then carry on from there rather than trying to hurry. So again, this is just to give you an idea about what kind of things one has to deal with. And you can make now the model very complex. You have if you have understood how to build the model starting from like halos. So you have to have halo, star cooling, star formation, IMF. At some point you can calculate luminosity match with observations. If that works well, fine. And then you go to massive stars, their merger, the gravitational wave events. So, okay, then that's all for today. I think, yeah. There will be a tutorial after this.